The last couple of lessons were quite long. This one is short, but it's one of the most important in the program. It will put the ideas developed earlier into a form we will use many times in the future. It is crucial that you are comfortable with the ideas it holds, because that means you will be comfortable with most of the maths we are going to meet later. Don't move on until you are confident that you understand the ideas well enough to be able to apply them in new situations. It's possible to extract the essential ideas from the majority of problems in a maths course and summarize them in a chart. Here it is. The chart is followed by an example illustrating how to apply it. When presented with a maths problem, you might find that it has a lot of words arranged in paragraphs or a simple diagram containing only a few symbols. In every case, the problem must contain 4 components. Sometimes they're obvious, but on other occasions you must either translate words or interpret symbols in order to find those components. If you look at the chart on the right, you will see the box at the top. That represents the problem and its 4 components. Begin by looking for the keyword. That will be one of the components. It might be at the start if the question says what is the value of, or it might be at the end. The keyword is a useful concept that is usually difficult to measure directly. You should build up a list of those commonly encountered in your maths course, such as perimeter, area, volume, or probability, percentage, gradient. Did you notice the first 3 are for shapes and the others are for comparisons? When you have found the keyword as part of your analysis, that leads to a set of formulas. They will usually begin with that keyword. The setting determines which measurements are relevant. For example, area is a 2-dimensional concept, but volume involves 3. The keyword and setting work together to indicate the relevant formula. So once you have found the setting and the keyword, the combined information they hold is the formula which is part of your solution process. So we go from the problem, analysis, finding the keyword and the setting. That gives us a formula to start our solution process. And the solution process is exactly the same as the one you have used many, many times before. The process of turning a formula into an answer or solution is simple. Just replace most of the letters by numbers, and these numbers will be supplied in the problem. So if we have a look at the problem, in there is mention of the data and the unknown. We extract those and apply them in this section of our analysis. We know that the question or task is not going to be a letter replaced, but the numerical data or relationships will be. And after replacing those, we have an equation with one letter. In other words, we have completed the substitution section of our three-step solution process. We do not replace the letter representing what the question wants to know. The problem must have information for all the others. Difficult problems supply information in the form of a relationship. For example, the height of a box is twice the width. That means you will replace the h in the formula you're working with by 2w. And hopefully the problem has given you a numerical value for w. So by the time we have read the problem, analysed it to find the four parts which must be present, we have a formula which has been converted into an equation with only one unknown. The solving part of the solution is basic algebra. It might be necessary to introduce a preliminary step by grouping similar terms. If the pronumeral is by itself in this equation, you evaluate it. Otherwise, you shift and reverse in order to isolate it. To ensure accuracy, we only do one process at a time. So we take it from substitution to get an equation with one unknown, using our standard solving technique to tidy that up into its simplest form, and we are left with an answer. And we know we have an answer when we have one letter and one number making the equation. So there is a diagram which shows our solution process. It applies to every problem in a maths course. Here is an example of applying it. The problem: what is the length of a rectangle which is 20 centimetres wide and has an area of 800 centimetres? So you can see the four components which were in our general representation: length, rectangle, width, area. Now the key words in that problem: area. Area is a general concept indicating size. But size of what? That's the setting. The setting for the problem is rectangle. There's clearly an unknown. What is the length? And there is data. 20 centimetres wide, area 800 square centimetres. The keyword reduces the number of formulas which might be relevant, but it does not give us the equation we need to work with. The keyword reduces the number of formulas which might be relevant. Of the millions which exist, we consider only those that begin with area equals. We don't use area as pi r squared or area as base by altitude divided by 2. They do not apply to rectangles. The formula we use, area is length by width. Now we have the appropriate formula. We know the problem must supply two facts, because this formula mentions three things, and if we're only going to have one unknown, the problem must have two pieces of data. That is consistent with what we found when we analysed the problem. So when we substitute the data, we replace area by 800, we replace width by 20, the missing component, the length, can be calculated. In this case, the L in our equation is not by itself. So we have to use our shift and reverse approach to isolate it. Our calculation, 800 stays where it is, the 20 moves, the multiplication becomes division, and we get the answer 40 equals L. Now we have a numerical value for our answer, 40 equals L, where L represents the length of this rectangle. But because it's a practical question, when it says what is the length, the answer must include units. And the units given in this problem were centimetres. So our answer is the length is 40 centimetres. Now, when you're confident that you understand what was covered in this lesson, you will have a mental view of mathematics which reduces the complexity of the subject enormously. Instead of seeing problems as individual items, you will see them simply as a modification of what you already know, which is summarised by the chart. Instead of you adapting to mathematics, you adapt the mathematics to your overview, which is the chart. Instead of carrying the solution to thousands of problems in your head, you carry one chart and all 1,000 problems can be fitted into it when required. We'll go on from there in the next lesson. See you then.